So we're starting late because we had a fire drill. So, hi Jason, everybody say hi Jason.
Hi Jason.
Yeah, see, there you go. And what we're going to do is to first of all take a look at last night's homework. And I want to do that for two reasons. One is that I want to make sure we have the right answers. And the other is that I want to make sure that we're showing our work correctly for this. Now, with that in mind, let's take a look at each of the questions that we had. The first question was, find the limit as x goes to 2 of 4 minus x squared over 2 minus x. Now, as we evaluate this limit, the first thing that we are going to do is to check to see whether or not I can do direct substitution on it. If I try to plug in x equals 2 directly here, because this is a rational function, maybe I could use the rational function theorem, what I get is 0 in the denominator. Oh, that's a problem. I can't use the quotient rule for this. So, instead, because my form is 0 over 0, this indicates that there is a common factor of x minus 2 that can be found here. Or in this case, 2 minus x. And so, because I have a common factor of 2 minus x, I can immediately use the alias theorem to replace my complicated function with 2 plus x. And this limit is the limit of a polynomial. I can immediately use the polynomial theorem and directly substitute, and we're done. So the key elements that have to happen here are, first of all, I have to check my form. And the reason I want to check my form is this. If I get some form like 3 over 5, that's my limit. But if I get a form of 0 over 0, that's telling me something very different. It's telling me that I can cancel a common factor.
So we'll have to show form is 0 over 0 and then...
Yep. I want you to show the form every time for now. Later on in life, you will do it mentally after you've gotten to where you're doing it all the time. The next question, like unto it, limit as theta goes to 0 of theta sine theta over theta. By the way, pronunciation here, this is theta with a th, theta. It is not theta, which is a kind of cheese. Okay. The first thing that I'm going to do is to check the form. And when I check the form, I see that I have 0 times 0 over 0. And so my form is 0 over 0. Put that form off to the left. It's not your limit. It's not a number. It's just the form. So we have this, which indicates a common factor. I can see that common factor coming a mile away. And so I have the limit as theta goes to 0 of sine theta. Now, sine theta is a continuous function. And so the value of that limit is simply the value of sine of 0, which is 0. And if you doubt that, think about the unit circle. Think about angles that are close to 0. They're going to produce sine values that are close to 0. My third limit presents us with an interesting algebraic challenge. The limit as h goes to 0 of x plus h quantity squared minus 2 quantity x plus h plus minus x squared minus 2x. All of that over h. Now, before I begin, I'm going to check the form. And when I check the form, I am checking what happens when h is 0. And when h is 0, this term collapses to x squared plus 2x minus x squared minus 2x. Hey, that's 0. And in the bottom, of course, my denominator is also 0. It probably doesn't surprise you that the form will be 0 over 0 for every one of these, and also for every one of the ones that you do for tonight. Next week, we're going to have forms like 1 over 0 that we'll call the infinite form. So for now, just check the form. Don't be surprised when it's 0 over 0. So this indicates that there is a common factor that I can cancel, but I don't see it. So that means that I'm going to need to do a little bit of algebra to find it. So I'm going to replace x plus h squared with what it is. And what is x plus h quantity squared?
Square plus square twice the h plus h.
That's it. So this guy is that. And 2 times quantity x plus h is the same as
2x plus 2h.
And then still minus x squared, still minus 2x over here. And then all of this is still divided by h. This has gotten a little ugly. Fortunately, this is the worst it gets. This is the point of maximum grossness for this problem. Because I observe that I have some like terms that can be combined. I have an x squared and a negative x squared. Those cancel. And I also have a 2x and a negative 2x. And those cancel. And now comes the wonderful moment that we have known was coming, and that is that when I look at all of the terms that are left in my numerator, I see that all of them have a common factor of exactly h, h, and h. And when I factor out that common factor of h, in the first term, I get 2x. In the second term, I have h left over. And in the third term, I have a 2. And those cancel. Now here's the last thing I want you to observe about this problem, and that is that now when h goes to 0, that does not affect the 2x or the 2. Those are both constants with respect to h. So that as h goes to 0, the result that I get is 2x plus 2. Good? Good. All of these, by the way, Claire, are going on the handout, so if I'm going a little fast, don't worry. Okay. The next one here, limit is y goes to 3 of 1 over y minus 1 over 3 over y minus 3. First, I'm going to begin by checking the form, and when I plug in y equals 3 here, I get 1/3 minus 1/3 is 0, and on the bottom, 0 also. We knew that was that. I observe that in the top here I have a compound fraction. 1 over y minus 1 over 3 all over y minus 3. And so we want to deal with that in some way. There's 2 almost identical ways that we can do that. One is to get a common denominator here, and then rewrite division as multiplying by the reciprocal. My favorite way to do it is to clear the fractions by multiplying top and bottom by the common denominator. And the common denominator here is 3y. So if I multiply top and bottom by 3y, like so, then in the top, I get 3y over y minus 3y over 3. Distribute. And at the bottom, I get y minus 3 times 3y. I'm not going to bother to simplify that unless I really need to. Aha! The point of doing this is that I have now cleared out my fractions, because that cancel is giving me 3. This cancel is giving me y. And I have turned my compound fraction into a simple fraction. You see?
Why don't you just
I can. It just takes me extra steps. If I did common denominator, which I can do, then what I end up with is the limit as y goes to 3 of 3
minus y over
minus y over 3y all over 1y minus 3.
then you just cancel it out.
And now, I rewrite division as multiplied by the reciprocal, and that gets me back to here. Either way is fine. I like this because I make fewer mistakes when I do this. I usually actually skip this step. I can see this in my head. Boom, boom, boom. Okay. So having done this now, I observe that I am guaranteed a common factor of y minus 3 because my form was 0 over 0. So I've obviously got a factor of y minus 3 here, but what about at the top? Where's my factor of y minus 3?
That's
Say more. Please, please.
y minus 3.
Yes, that's right. 3 minus y is the same as negative 1 minus 3. And now my common factor cancels. I let y go to 3, and I get negative 1 over 9, and we're done. For the last one, we have, I forgot what the last one was. Yeah. The limit as t goes to negative 1 of t cubed plus 1 over t plus 1. Where do I begin?
Check.
Check the form. And when I plug in t equals negative 1 into the top, what do I get?
0.
And bottom? Okay, so my form indicates common factor. This is the indeterminate form. Okay, well, it's pretty obvious where my factor of t plus 1 is there, but what about here? I have to find what that factorization is, and I can either do it by long division or by synthetic division. And it's your choice. Long division is going to look like this. If I divide t plus 1 into t cubed plus 0t squared plus 0t plus 1, then I'm going to ask, how many times does t go into t cubed? And the answer is not 3, not 3. Multiply and subtract. How many times does t go into negative t squared? Negative t. Multiply and subtract. Don't forget to change your signs. How many times does t go into t? 1 time. And it goes evenly with no remainder, as we knew that it had to. So that allows me now to rewrite t cubed plus 1 as t plus 1 times the quotient of t squared minus t plus 1. And now if I let t go to negative 1, I can use the alias theorem to cancel out my common factors. And I get a polynomial, which I can evaluate by direct substitution. 1 plus 1 plus 1 is 3. If I had used synthetic division to divide, then I would have used substitution value of negative 1, multiply, add, multiply, add, multiply, add. And the way in which you interpret this is, here's my remainder, which is 0, which I knew was coming. Here are the coefficients of my reduced polynomial, t squared minus t plus 1. In the wild, you can see that I definitely prefer this over that. To such an extent that I don't do long division unless I really have to for some reason.
So we'll try it out.
steps for when we reach conclusions.
No, that's fine. Yep. If you know a difference of cubes or sum of cubes factoring pattern, then it's all in one. So you're good. I don't need to see algebraic steps. I need to see calculus steps. So the calculus steps happening here are the limit equals cancellation equals 3. Do you like that? Okay. Questions, comments, or calculus jokes? Okay. Awesome. Well, I would like to take a look now at a technique, an algebraic technique, that expands our reach a little bit. It's called rationalization. And rationalization is not a calculus thing so much as it is an algebra thing. It is an algebraic technique that reveals hidden factors. And it goes all the way back to the stuff that you did probably in Algebra 2 or maybe last year in Trig. My guess is that because Ms. John, who is old school, was your teacher, that she probably had you rewrite 1 over the square root of 3 in a different form. No? She didn't care. You forget. Does anybody remember having to do
Well, I did like the
something like this? When you were in China, you had to do that. That's right, right. Does anybody know why?
There's like square root in there.
Why not?
That's the other program.
Ah, yeah, well, there's actually a reason for it, but that reason is a little out of date. Here it is. Imagine a world before calculators. I call that BC, before calculators. And before calculators, we had to do computations by hand. And imagine that you have this expression, 1 divided by root 3. So if you're going to do this expression by hand, then what you're going to have to do is to take some approximation for root 3, and you're going to have to divide that into 1. Okay? So then you've got to do like 4-place division. That's horrible. It's going to take you a long time. But if I can rationalize now, look at what my division becomes. That's a lot easier, isn't it? The reason that rationalization was necessary in the BC era was that it made hand computations, pencil and paper computations, a whole lot easier. It was a question of efficiency. It wasn't that there are some natural rules that you can't have square roots and bottom. It was that you didn't want to, because it would make your life hard. Then, in the 70s, 80s, battery-powered calculators started coming onto the market. By the time I was in high school, so I started out with 2 in 1985, if you can imagine that. And at that time, you could get a fairly large, clunky handheld calculator that could do 4 functions, square roots, tangents, sines, cosines, that kind of thing. But it was expensive. And they got cheaper. The next year when I had chemistry, you could get one from Casio that had conversion factors built into the side. And that was awesome. And then they just continue to get, well, now you can get a graphing calculator for $85 on sale that has more power in it than any personal computer had in the 80s. And it's cheap. Well, if you have that, then there's no need to distinguish between 1 over root 3 and root 3 over 3. So all of us people that are kind of in new school way of doing things, we don't care about our forms too terribly much. You can give us this one, and you can give us this one, and they're the same thing, and we don't really care. But the technique of rationalizing, where you rationalize the denominator or maybe the numerator, still remains useful because it reveals hidden factors for us. And let me show you how. Consider this limit right here. the limit as x goes to 2 of root x plus 7 minus 3 all over x squared minus 4. Now this looks like a fearsome limit. So we are going to begin by considering what is the form of our limit. And we plug in. What is the square root of 2 plus 7? Minus 3 is? And in the bottom, also 0. So there is a common factor of x minus 2 in here somewhere. But I don't see it. Do you see it? It's hidden. In the bottom, I can see that that's x minus 2 times x plus 2. But in the numerator here, I don't see an x minus 2. So we're going to find that by leveraging our difference of squares factoring pattern. Way back in Algebra 1. Who did you have for Algebra 1?
Mr. Booker.
Ah. So, Mr. Booker, I am sure, taught you a minus b equals a plus b is minus b squared. That's right. Right. And the magic of the difference of squares factoring pattern is that it is literally the only squares factor, the only quadratic factoring pattern that has no real term. Okay. And we're going to leverage that by considering this to be our A, considering this to be our B, so that if I multiply top and bottom by a plus B, lo and behold, we're going to get the square root to go away. Not go away entirely. It's just going to transfer itself. Good. Very simple. There we go. Now, this quantity here, a plus b, is called the conjugate of a minus b. The same two terms with the sign changed. And so what we are doing is multiplying top and bottom by the conjugate in order to make use of the difference of squares factoring pattern. And when we do, look at what we get. We get a squared, the square root of x plus 7 squared is x plus 7. Minus b squared is 9. And all of that down here is x squared minus 4 times root x plus 7 plus 3. I am not going to simplify that. I don't have any need to simplify that. I'm simply going to let it be what it is. But now when I clean up the top and factor the bottom, because I know I need a factor of x minus 2, look at what happens. In my denominator, I still have all of this. In my numerator, look at that. I have x plus 7 minus 9 is the same as... There's my hidden factor. Look at that. It's not magical. Things cancel. And now I have a limit that can be evaluated by direct substitution. Because my form is no longer 0 over 0. The common factor of x minus 2 has been canceled out. And I get 1 over, that would be 4 times, what's the root of 2 plus 7? 3 plus 3 is 6. 1 over 4 times 6, or 1 over 20. That's pretty cool. Why don't you try one? Evaluate the limit. for the purposes of the video, I will pause recording so that you can practice at home. Okay, let's see what you guys did. Tell me how it goes.
Okay. I'm the phone first.
Bingo! Good for you. Excellent. Okay, now what?
Limit x to 1. Multiply the whole equation by square root x plus 3 plus 2 over x plus 2.
Square root of, yeah. Good. Very good. Clara.
So you get the 2t minus 3
Sorry.
square root t plus 1 over t plus 3 minus 1. It's t minus 1.
And it is okay with me if you are able to do those kinds of calculations in your head. I don't need to see a lot of intermediate algebraic detail. Now what? Mark.
Back out the 0 top, so it's 3 times t minus 1.
Wow, I just keep on trying to make a mess of that problem, don't I? Okay.
Times the square root. Yeah. And you can cancel out the t minus 1. And then we can plug it on. And you get
Good. So notice that in contrast to our previous problem, here we rationalized the denominator. In the previous one, we rationalized the numerator. Hey, no big deal. I was tempted to create an interesting problem, but as I thought it through, I realized it would require something we don't know yet. I was going to do them involving sines and cosines, but not just yet. Well, there it is. So to sum up, when we are evaluating limits, in the big picture, we can read them off of graphs. You guys are pretty good at that at this point. And that can include the graphing calculator. All of this gives us estimates, and it opens us up to the potential possibility that maybe the graph is lying to me in some way or another. Okay? So it's an estimate, and it needs to be treated with caution. Or we can appeal to our properties and theorems. We have our big 5 limit properties. Well, I'd say 5. We really have 6 if you count the constant multiple rule, plus the 2 direct evaluation rules. So we have constant rule and linear function rule, LFR, linear function rule. And then we have some, I'm just going to write this in shorthand, sum, difference, product, quotient rule, and power rule. The limit properties give us exact analytic answers, assuming that our functions are well behaved. And in particular, the problem that we have to watch out for with the quotient rule is the possibility that we have a zero denominator. So when we have a zero denominator, we have a second tool in our arsenal, and that is we can use the alias theorem. Now, Beth in the other class asked a really good question. Is the alias theorem only useful when you have quotients with zero denominators? And actually, no, it's useful under a wide variety of circumstances. So our alias theorem is useful anytime we have 2 functions that are equal except at c. So for example, if I have f of x equals x squared plus 3, where x is not equal to 2, and I ask what is the limit as x goes to 2 of f of x, Well, I know a function that is equal to f except when x is 2, and that is x squared plus 3. So that I can replace f of x with its alias function, x squared plus 3, which is exactly equal to f except for x is at 2, and evaluate this limit now directly, giving us that. So that's a use of the alias theorem in which there is no cancellation or anything involved. Here, this guy. Okay. So the idea is I have a function which basically is a quadratic parabola, except that it's going to have a hole right here at x equals 2. Okay. And I ask, what is the limit as x goes to 2 of f of x? And because this is not a polynomial, polynomials don't have restricted domains, I can't use the polynomial theorem. However, I do know a polynomial that is equal to f at every x except at x equals 2. So I can replace f with that alias function. Here's f, here is g. F equals g, except at x equals 2. So I can replace f with g and evaluate the limit of g, which is guaranteed to be equal to the limit of f. When we applied our limit properties consistently, we also ended up with two very useful theorems, the polynomial theorem and the rational function theorem. And both of these are direct substitution theorems. If I have the limit of a polynomial, if I have the limit of a rational function, I can directly substitute as long as I'm not dividing by 0. More precisely, the limit as x goes to c of phi of x is equal to p of c for any polynomial. And the limit as x goes to c of p of x over q of x is equal to p of c over q of c for any polynomials p and q, as long as q of c is not 0. So this is a full summary of what we have so far for limits. We're going to add a little bit in the way of techniques, but this is the vast majority of what we're going to be using, our kind of bread and butter techniques for limits. Does that make sense to everybody so far? Very good. Well, bell's going to ring, and I will see you on Monday.